Welcome back guys to Embedded Systems course. So have you ever used a microwave, smartwatch or even a car with automatic headlights? Then you have already interacted with embedded systems, the hidden technology driving most of today's smart devices. So in this module, we will introduce you to the world of embedded systems, what they are, where they are used, and why they so matter. So let us get into the agenda first. So here's what we will cover in the lesson. First, we will define the embedded system. Then we will explore its components and look at everyday examples. After that, we will compare the embedded systems with the general purpose computers. Then finally, we will understand why embedded systems are so important, especially in industries like healthcare, automobiles, and IoT. So let's go. First, we'll see what is an embedded system. So it's a computer, but not the kind you use for browsing the internet or editing documents. So an embedded system is a special purpose computer built to perform one or a few specific tasks. It's usually part of a larger machine or device. For example, your microwave has a tiny computer inside that controls the timer, the power levels, the turnable, and that's an embedded system. Think of a general purpose computer like a Swiss Army knife. It can do many things at once. So now think of an embedded system as a precision screwdriver. It's designed to do only one job, but do it extremely well. It doesn't need to open web pages or play music. It just has to get its job done reliably and efficiently. Now let us see the components of an embedded system. So first, there is the microcontroller or the microprocessor. This is the brain of the embedded system. Then there's memory used to store the software and data. Then input devices like sensors, buttons or switches allow the system to detect the environment or use commands. Output devices like motors, buzzers or displays perform the action, and finally there's a software often called as firmware which runs the logic. So all of this is typically packed into a small circuit board. So let us now move on to the types of embedded system. So embedded systems comes in different forms based on the complexity. The first one is the small scale system are found in the TV remotes or the calculators. Then we have medium scale systems exist in washing machines or TV cameras. Then we have complex embedded systems power things like aircraft, medical devices and smart cars. Their size may vary but their core purpose is the same, dedicated and efficient control. Now let us move on to see some examples of daily life. So embedded systems are all around you. In your home, your refrigerator, smart TV, washing machine and microwave all have embedded controllers. In healthcare, devices like ECG monitors, insulin pumps and even hearing aids are powered by embedded system. In cars, systems like anti-lock braking, airbags and infotainment are also embedded control. In factories, embedded systems manage robotic arms and assembly lines. And finally, in communication, for the routers, satellites, and even your mobile phone's internet controls rely on embedded technology. Now, let us move on to see some real-world use cases. So let's take a simple example, a washing machine. You select a program and press start. And then what happens next? The embedded system checks the water level, controls the valve, sets the speed, and hits the water and runs the washing cycle. So all of that is handled by a pre-programmed controller without you doing anything else. Now, let us see embedded system versus computers. So what is the actual difference? So here is the one. Embedded systems are designed for a specific task, whereas the regular computers are built for general purpose tasks. So embedded systems are limited in terms of flexibility to one thing pretty well. And in the case of regular computers, they are very flexible and can run multiple applications. Embedded system often lacks a screen or a keyboard, but a regular computer typically has a screen, keyboard, and a mouse. Then embedded system uses less power. And here in the regular computers, it requires more power for general tasks. So embedded systems are limited, I repeat, embedded are very limited memory and usually programmed once, whereas regular computers have large memory and regularly updated or programmed. Now, let us move on to why embedded systems matter. For starters, they enable automation from start fans, I repeat. So for this, enable automation from smarter fans that adjust speed automatically to irrigation systems that water plants only when the soil is dry. Also cost effective, you don't need a full-fledged computer for simple tasks. They are very reliable, built to run for years without failure. Most importantly, they enable real-time processing like deploying airbags in a fraction of a second during a crash. And with the rise of IoT, they are becoming even more critical. So let us now get to see what are embedded systems in IoT. The Internet of Things refers to a network of interconnected devices that communicate and share data to create smarter systems. At the core of the smarter devices are embedded systems which enable them to perform specific tasks, process data, and interact with each other. So how embedded systems power IoT? The first one is data collection. Embedded systems in IoT devices collect real-time data through sensors to monitor conditions and gather information. Then we have decision making. These systems analyze the collected data, make decisions based on preset rules or algorithms, and take actions such as turning on a light or adjusting a thermostat. Then we have communication. Embedded systems allow IoT devices to communicate with each other, cloud platforms. So this connectivity enables devices to share data, receive updates, or send commands. Then we have energy efficiency. Since embedded systems are designed for specific tasks, they are highly optimized for the power efficiency, ensuring that IoT devices can run for longer periods without draining much energy. Now, let us move on and see why we should consider a career in embedded systems. So the first one we have is software and hardware integration. So there are exciting and versatile fields combining both. Then there is a very high demand for embedded system as a career. So opportunities in automotive, telecom, consumer electronics, robotics, and IoT. Then we have real world impact. So develop the techs like the smart devices and medical equipment. Then we have innovation. It is ideal for those who enjoy creating practical solutions. Then we have versatile skill set, which is expertise in both software and hardware. Then we have growing opportunities, the strong career prospects with IoT and automation. Then we have diverse roles, so positions in product development, system design, and firmware. Then we have job security. This is the long-term demand in emerging technologies. So in short, if you love solving real-world tech problems, embedded systems offer a dynamic and promising career. So then we have high demand. In industries like IoT, automotive, and robotics, with companies like Honeywell, Google, and Qualcomm hiring engineers. Then the salary range we have is 1.3 LPA to 18 LPA as an entry-level engineer. Then for 5 LPA to 12 LPA as a mid-level engineer, and finally 25 LPA to 40 LPA in the senior roles. And then we have real-world impact, that is a combined software and hardware to develop the innovative technologies like IoT devices and self-driving cars. Then we have a growing career path. So with strong demand and evolving technologies, embedded systems offer a rewarding and a dynamic career. So let's have a quick recap of this. So embedded systems are computers designed for specific tasks. They are everywhere in your home, car, hospital, and even in your pocket. They are different from computers, they are simpler, cheaper, and more focused. They are critical for automation, safety, and IoT. And they are only going to become more important in the future. So let's now move on to the next module. Welcome back to our Embedded Systems course. In the last module, we explored what embedded systems are and how they're part of our everyday devices. But designing and building embedded systems comes with its own set of challenges. So in this module, we will explore the three biggest categories of challenges in embedded system development. So before proceeding, let's see what we are going to cover in detail. The first one is limited resources. We'll understand the challenges with the memory, power, and storage in embedded devices. Then we will move on to the real-time requirements, that is why timing is critical in embedded applications and how missing a deadline can be dangerous. Then we have the reliability and safety. So why these systems must be ultra reliable and how international safety standards help ensure that. So let's begin with the first challenge, that is the limited resources. Unlike your phone or laptop, embedded systems are built to do more with less. So most embedded devices are small, affordable, and highly specialized. To achieve this, they are built with very limited resources. This includes very less RAM. Then we have tiny storage space, that is for ROM or flash. Then we have minimal processing power, and then finally we have limited battery or energy source. Now why it is like that? Because they must be cheap, compact, and energy efficient. So let's now move on to see the first challenge for the power consumption and battery life. So, most embedded systems are used in the battery-powered devices like smartwatches, fitness bands, then we have remote controls and wireless sensors. So, these systems need to last for weeks or months on tiny batteries. So, developers face two major power challenges. The first one is minimize power usage. The system must consume as little power as possible, especially when idle. That's why low power models like sleep or dead sleep are used. Then we have optimize the processing time. The faster the processor finishes a task, the sooner it can go back to sleep, saving energy. So in short, embedded systems must be smart about energy use. Every milliampere matters. Then we have the second challenge, that is limited RAM memory. So RAM is a temporary memory that stores data while the system is running. In embedded systems, RAM is extremely limited, sometimes just 2 kilobyte or 8 kilobyte. So compare that to your phone, which may have 8 GB of RAM, a million times more. So with so little memory, developers must avoid the unnecessary variables. Then they must use lightweight code. Then they should avoid memory leaks or inefficient loops. One small error in RAM usage can crash the entire system. So memory management is a key skill in embedded programming. Let's now move on to the third challenge. Limited ROM or flash storage. Or flash memory is where the embedded system software or firmware is stored. The memory is also very limited, sometimes 32 kilobyte or 128 kilobyte. So developers must compact optimized code. They should avoid large libraries or unused features. They should use the efficient data storage techniques. So there's no space for bloated programs or unnecessary functions. Every matters. That's why most embedded systems are written in or assembly, because these languages gives developers full control over how memory is used. So let's now move on to the fourth challenge, that is the processing power limitations. So embedded systems don't have powerful CPUs like laptops. So many use bit or 32-bit microcontrollers, which are very limited processing capability. This means you can't run heavy tasks like video processing or AI models unless the system is designed for it. The code must be lightweight, fast, and focused. So the challenge is to build efficient logic that solves the problem with minimum resources. Then we have real-time requirements. What does it mean? So in many embedded systems, it's not enough to just get the job done. It must be done on time. A real system is one where tasks must be completed within a fixed time limit. For example, an airbag must inflate within milliseconds of a crash. A medical monitor must show real-time heart activity. If the task is delayed even by a second, the system may fail its purpose. Then we'll see why timing is crucial. So real-time performance is critical in many industries. The first one is automotive. For systems like ABS or lane, timing is everything. Then medical devices like pacemakers or ventilators must work in real time. Then we have aerospace. Any delay in control system can be life. So in such systems, the challenge is to guarantee the response time, no matter what. So this means optimizing not just the code, but also the hardware and operating system. Then we have types of the real-time systems. So there are basically two types of real systems. The first one is hard real-time. Under this, these systems must never miss a deadline if that serious failure or danger can occur. For example, airbags, pacemakers, industrial robots. The second one is soft real-time. Occasional delays are tolerable, but performance may drop. Examples like video streaming, voice recognition. In soft real-time systems, a short delay is okay. In real, there is no room for error. Then let us understand the reliability, why it matters. So embedded systems often need to run for years without crashing. You don't want your washing machine or ATM to fail randomly. So in critical systems, failure can be dangerous. Imagine a ventilator suddenly restarting or a robot arm going out of control. So embedded systems must be tested under all conditions, including temperature, humidity, vibration, and long operation. They must recover from errors, handle powerful failures, and log issues for the diagnostics. So let us now move on to understand the safety in embedded systems. So safety is about preventing harm to people, property, or the environment. So embedded systems in cars, trains, airplanes, and hospitals must follow the strict rules. So safety is ensured through the redundant systems, that is the backup hardware or logic. So then we have watchdog timers to restart the system on hang. Then we have emergency shutdowns. So testing for safety is not optional. It's required by international laws. Then we have the global safety standards. So these are the global standards that every safety critical embedded system must follow. The first one is IEC 262 for the automotive electronics. Then we have IEC 61508 for industrial systems. Then we have DO 178C for the avionics software aircraft. Then we have IEC 62304 for the medical software. So these standards ensure that the system is designed, tested, and verified before it's used in the real world. For developers, this means writing cleaner code, testing rigorously, and documenting everything. So let's now have a recap of what we have learned. So let's quickly summarize. The first one is limited resources mean developers must write efficient, optimized code. Then we have real-time requirements mean tasks must be completed within strict time limits. Then we have reliability and safety are non-negotiable. In critical systems, failure can lead to danger. So overcoming these challenges is what makes embedded systems both complex and exciting. So let's move on to the next module. Welcome to the chapter 3 of our embedded systems course. So in this session, we'll talk about the brains of embedded systems, the microcontrollers and the processors. So here's what we will learn in this module. We'll first see what is a microcontroller. Then we will see the difference between a microcontroller and a microprocessor. Then why microcontrollers are important in embedded systems, and then we'll see what is a processor cycle, and then finally we'll see the role of the processor in a microcontroller. So let's get started. So let's move on to understand what is a microcontroller. A microcontroller is a small computer on a single chip. It contains there is a central processing unit. Then it contains RAM, there is a random access memory, the temporary memory. Then we have ROM or flash, that is for the storage, that is a read-only memory. Then we have input or output ports, and even sometimes we have timers, ADCs, and communication interfaces. So all of this is packed into a single integrated circuit, often smaller than a coin. So in simple words, a microcontroller is like a tiny brain that can take input, process it, and give the output all by itself. So let's move on and see the real life analogy. Think of a microcontroller as a self-contained robot that is basically a simple computer on a single chip. It has eyes and ears, that is the sensors as input. It has a brain, that is a CPU for processing. Then it has voice, that is the output. So everything is built in. It doesn't need the external components to function. That's why microcontrollers are perfect for the embedded systems that do one job very efficiently. So let's now see the difference between a microcontroller and a microprocessor. So in terms of purpose, a microcontroller does a specific task and a microprocessor does the general purpose computing. So microcontroller has CPU plus RAM plus input-output devices, and a microprocessor only has CPU. The cost for a microcontroller is very less, and for a microprocessor it is higher. The power consumption of a microcontroller is very low, and a microprocessor it is very high. The size of a microcontroller is very compact, and the microprocessor is larger, needs more chips. Then microcontroller is used in the embedded systems and the microprocessor is used in the computers and the laptops. So a microcontroller is like a compact toolkit with everything inside, and a microprocessor is like a CPU that needs the external ROM and the input-output devices to work. So let's now move on to see the visual explanation. So imagine building a radio. With microprocessor, you buy separate components like processor, memory, storage, ports, and wire them together. So with a microcontroller, everything is already in one chip. You just program it and use it. So that's why microcontrollers are simpler and more suited for the embedded systems. So now let's move on and see the importance of microcontrollers in system. So embedded systems often need to run a specific task, be compact and affordable, use very little power, run for years without an error. And microcontrollers are perfect for this because they have low cost, can be battery operated, come with all the components already built in, and they are reliable and easy to program. So that's why you will find microcontrollers in everything from washing machines to drones to heart rate monitors. Let's now see the common microcontroller applications. So here are just a few examples of when microcontrollers are used. The first one is microwave, that is the controls timing, heating and display. Then we have car, it manages airbag, sensors and auto wipers. Then we have camera that adjusts the focus and shutter automatically. Then we have Bluetooth earphones, it handles the audio and the battery. Then we have the smart light that receives input from application and changes brightness. So in each of these, the microcontroller runs a single focus based on the user input or sensor feedback. Let's now move on and see what is a processor cycle. So let's now understand how a processor inside a microcontroller actually works. So every controller runs in a loop called the processor cycle, which includes three main steps. The first one is fetch, that is get the instruction from the memory. Then we have decode, that is understanding what the instruction is. Then we have execute, that is to perform the action. So this loop happens millions of times per second, allowing the controller to read the input, process data, and control the output in real time. So the real world analogy, we have the processor cycle. Then we have the role of the processor in microcontroller. The processor is the core decision maker in a microcontroller. It does things like reads data from the sensors, that is for example temperature. Then it compares the values or runs calculations. Then it sends signals to the motors, displays or alarms, and then it stores the important data or settings in memory. Think of it like the brain of the system, deciding what to do, when to do it, and how to react to the environment. So let's now move on to see the processor having complete control. But the processor alone is not enough. It works with the peripherals like ADC. So then let's move on to see the processor plus peripherals is equal to complete control. But the processor alone is not enough. It works with the peripherals like ADC. It works with ADC, that is analog to digital converter. Then we have timers, and then finally we have serial ports like UART, SPI and I2C. These peripherals help the processor interact with the real world to read voltage, measure time, or send data to other devices. That's what makes a microcontroller such a complete and powerful solution in embedded systems. So we have certain key takeaways. So let's recap what we have learned. A microcontroller is a mini computer with a CPU, memory, and input-output in one chip. A microprocessor is just a CPU. It needs external components. Then we have microcontrollers are perfect for embedded systems as it is compact, cheap, and low power. The processor cycle includes fetch, decode, and execute. The processor is the brain, but it works with the peripherals to control the device. So microcontrollers are all around us. They make our devices smart, efficient, and interactive. So by understanding how they work, you are opening the door to a whole world of innovation, electronics, and automation. See you in the next module. Hello and welcome back to the module 4 of our Embedded Systems course. In the last few modules, we explored the components that bring embedded systems to life. But today we were diving into the core of the system, the processor itself. More specifically, two major architectural structures that shape how processors work. So, first we will see CISC, that is the Complex Instruction Set Computer, and then we will get to know about RISC, that is the Reduced Instruction Set Computer. By the end of this module, you will know what makes these architectures different, where they are used, and how to choose the right one for your project. So, let us now move on and see what is CISC. CISC stands for Complex Instruction Set Computer. It is a type of computer processor architecture that is designed to complete tasks with fewer lines of assembly code by using the complex and the multi-step instructions. This reduces the number of instructions needed to write a program, which was super helpful back in the days when memory was limited and expensive. Most instructions in CISC are variable in length and complexity. The hardware must be smart enough to decode and execute them, even if they involve multiple steps internally. Then we have advantages of CISC. So what makes CISC useful in embedded systems? First, it allows the compact code. Because each instruction does more, programs can be smaller, which saves memory. Second, it has a built-in complex operation, so you don't need to manually code every step. Third, the CISC processors often have strong backward compatibility. Your old code still works. That's especially useful in the industry and legacy systems. Then let's understand these advantages of CISC. It's not perfect. The hardware is more complex, which means higher power consumption and more heat. Downside for battery-powered devices. Instructions take longer to decode and execute, making it harder to design high-speed pipelined processors. Because instructions vary in size, timing is inconsistent, which is not ideal for real-time systems. Then we have examples of CISC in action. So where do we see CISC? The most popular CISC architecture is x86, used in Intel and AMD processors for the PCs and industry controllers. Embedded system, the 8051 microcontroller, a CISC-based chip, is still used in washing machines, medical devices, and automotive electronics. It's not flashy, but it's reliable and cost-effective. Then let us see what is RI is like having a set of simple, fast tools instead of one complicated multi-tool. Each instruction does only one thing, but it does it quickly, usually in one clock cycle. The idea is keep instructions short, predictable and uniform, which makes it easier to build fast and efficient pipelines. You might need more instructions to get a job done, but each one is lightning fast. So let's now see the advantages of RISC. Fixed length instructions can be pipelined easily, speeding up the performance. Power efficient, which makes it ideal for battery-powered devices and sensors. And it's hardware friendly. RISC processors are simpler to design and scale across performance levels. That's why RISC dominates in mobile, IoT, and the real-time embedded systems. Then let's understand the disadvantages of RISC programs can be larger since complex operations are broken into simpler steps. They also depend heavily on good compiler optimization, so if your compiler is not great, performance may suffer. And finally, RISC uses separate instructions for loading and storing data, which can increase the memory traffic. So let us now move on to the examples of RISC in action. So it is everywhere. The ARM Cortex-M and A series power your smartphones, smartwatches, and even the Raspberry Pi boards. The open source architecture is gaining traction in drones and low-cost IoT chips. So even routers and set-top boxes still use MIPS, a classic RISC architecture. So let's now move on and see the versus RISC, the face-off. So let's compare the two side by side. So CISC in terms of instruction style is very complex compared to RISC. Then CISC in terms of execution speed is slower per instruction and RISC is faster per instruction. The code size for is smaller, but the code size for RISC is larger. The power efficiency in CISC is lower. The power efficiency in RISC is higher. The hardware cost of CISC is higher and the RISC is lower. So CISC is ideal for legacy industrial systems. RISC is basically made for IoT, the real-time and mobile. So after we have a knowledge of this difference, let us see the use cases of embedded systems. There are some real-world scenarios. An industrial controller running legacy code might use a CISC-based Intel X board. A smartwatch would almost always use RISC-based ARM Cortex-M processor. A drone doing real-time navigation and object detection, likely powered by for its speed and customization. So every system has its own priorities. The power, performance, and compatibility. So, the next question arrives, how to choose the right one? So, here is a quick checklist to help you choose. If you want a longer battery life, choose RISC. If you need to run the old software, choose CISC. Building a real-time controller, then use RISC. If your building a memory is super limited, then use CISC. If you want free and flexible architecture, there's no right or wrong. It's all about what your system needs the most. So let's now have a quick takeaway. Let's summarize what we have learned. So CISC is the compact code, complex hardware for legacy. RISC is simple, fast, power efficient for embedded and IoT. Both have their strengths and the choice depends on your application's goals. You now have the knowledge to make an informed architectural decision for your next embedded system. So let's now move on to the final module. So in this last module, we will uncover one of the most critical yet often overlooked, the pillars of embedded system, that is a memory. So here's what we will explore. We will first see the difference between the volatile and the non-volatile memory. Then we will see the various types of memory used in the embedded systems. Then we have memory architecture styles like the von Neumann and Harvard. Then we have real-world implementation techniques that boost performance and efficiency. And then we have smart memory management strategies for embedded environments. By the end of this module, you will know exactly how embedded devices store, access, and manage the data they need to function reliably. So even with the tight constraints on power, space, and processing power. So let's now move on and see the foundation of everything, that is a volatile versus non-volatile memory. Let's start simple. Volatile memory like RAM is fast and temporary. Volatile memory like RAM is fast and temporary. It forgets everything when the power goes out. Non-volatile memory like the ROM and flash is just the opposite. It's slower but remembers everything even when powered off. Think of it like your brain. RAM is like your short-term memory where you store today's to-do list. Then we have ROM, that is a flash, is your long-term memory where you have stored your name, your birthday, and how to ride a bike. This difference is at the core of how embedded systems make decisions, store instructions, and hold on to essential data. So this difference is at the heart of how embedded systems make decisions, store instructions, and hold on to essential data. So let's now move on to see the types of embedded system. So let's break down the memory types you will often encounter in the embedded systems and where they are used. The first one is SRAM, that is static RAM. The fast, stable, and used for registers and internal caches. It's expensive, so used in the small amounts. Then we have DRAM, that is dynamic RAM. So slower than SRAM but more affordable and denser. You will find it in the applications that need larger RAM. Then we have EEPROM, that is the electrically erasable memory. Good for storing small bits of data like calibration, values, or device settings. Then we have NOR flash. It is great for storing code. It allows random access and the execution in the place, it is the XIP. Then we have NAND flash, common in the SD cards and USB drives. It is dense and cheap, great for storage but slower for direct execution. So each of this memory type is like a tool in a toolbox. The trick is knowing which one to use when. So let's now see the memory architecture in embedded system. So memory is not just about what you use, it's about how it's organized. There are three main characteristics, I repeat. There are three main architectures you will find. The first one is von Neumann architecture. The code and the data share the same memory and bus. Simpler and flexible but limited by bandwidth. Then we have Harvard architecture. Separate memory and buses for code and data. This allows parallel access, faster and more efficient. Then we have modified Harvard, the hybrid that combines both of, Then we have modified Harvard, a hybrid that combines the best of both the worlds. This is what most modern microcontrollers use. So a von Neumann system is like a single lane road shared by cars and bikes. It can get crowded. On Harvard, the two separate lanes, one for cars and one for bikes. No slowdowns. So let's now move on and see the real world memory implementation. So let's talk about the real applications and the optimizations. The first one is XIP, that is execute in place. So instead of copying firmware into RAM, the MCU runs it directly from flash. It saves the RAM, speeds up the boot time. Then we have shadowing. The critical code is copied from flash so it can run much faster from RAM. Then we have external memory interfaces. So some systems connect to the external PSRAM or flash to expand the memory without adding cost to the chip. Then we have cache and prefetch buffers. So these help bridge the speed gap between memory and processor without the developer doing much. So all these techniques help embedded devices run faster and smarter without needing the massive hardware upgrades. So let's now move on to see the memory management techniques. So finally, let's look at how memory is managed on a day-to-day basis within embedded applications. The first one we have is static memory allocation. So predictable and safe, perfect for the real-time systems where dynamic allocation is risky. Then we have memory pools. So if it is efficient and fast, your pre-allocate blocks and reuse them, avoiding the fragmentation. Then we have DMA, that is direct memory access. So it moves data from memory to peripherals and vice versa without involving the CPU. It is, I repeat, huge power saver. Then we have wear leveling. So it is essential for flash memory, spreads out write or erase cycles to prolong the life of storage. Then we have low power memory modes. So many MCUs let you retain only critical sections of RAM during sleep to save energy. Then we have another one, that is ECC, that is error correction code, especially useful in the automotive and the medical systems where reliability is non-negotiable. So each of these techniques can drastically improve the system's stability, power efficiency, and lifespan. So from the smallest temperature sensor to a complex drone flight controller, memory is the silent hero behind embedded systems. So guys, congratulations on completing your journey into the embedded systems. You know you have a solid understanding of what embedded systems are, how they differ from general computing, and why they're essential in everyday devices. You have explored the key challenges like limited resources, real-time requirements, and the need for reliability. You have learned about microcontrollers, the difference between the CISC and the RISC architectures, and how memory is managed in these systems. With this knowledge, you are well equipped to start building the efficient, intelligent devices. This is just the beginning. Keep exploring, keep innovating, and let your ideas come to life. Thank you guys for watching.
Staying ahead in your career requires continuous learning and upskilling. Whether you're a student aiming to learn today's top skills or a working professional looking to advance your career, we've got you covered. Explore our impressive catalog of certification programs in cutting-edge domains, including data science, cloud computing, cybersecurity, AI, machine learning, or digital marketing. Designed in collaboration with leading universities and top corporations, and delivered by industry experts, choose any of our programs and set yourself on the path to career success. Click the link in the description to know more.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.